Hello and welcome back. This is episode 5 of solving some Rosetta code problems in Mathematica. So for those who don't know, rosettacode.org is a website where certain tasks are defined and people show off how that task would be solved in their programming language. So for example, this 15 puzzle solver is solved in all these programming languages. So in total, let's say 25 programming languages in which this certain task has been solved. So there's a list specifically for Mathematica or the Wolfram language if you want to look that one up, where some of them are implemented, but these are not yet implemented. So I selected a few of them, and the first one looked interesting because of its name, Eban number. So I thought first one it was referring to the IBAN number, so the international banking bank account number, so whatever it is. But actually it is not about that. It is about numbers that have no letter E in it in the English spelling. And so IBAN number, so the E is banned basically. And so basically show basically all the Eban numbers below certain ranges and count them. And the biggest range is 10 million, so it should be, reasonably performant to do that task. All right, let's have a look at how other people do it. That can inspire us. So they look at the, let's say, multiples of 1,000, million, and billion. So if you look at, basically if it has any 100, then it will not work, right? So 100, 200, 300, 400, up to 900. So for every multiple of 1,000, you can only go up to 100,000 or 100 million or 100 billion. And also for the ones, let's say, you can only go up to 100, 99. Because after that you always get 100, 230 something or whatever. So that's why, so I'm not really familiar with this code, but I guess this is modulus, I would guess. Well, we can have a look in nim perhaps. So the modulus and the quotient, let's say, divisor. Let's have a look at what other people do. So there's different people that do have different solutions. Let's go all the way up again. Let's see if there's a small code. For example, this one. This looks quite compact. So they take how many millions and the remainder, how many, billions, millions, thousands. And then they look if it's between 30 and 66. I don't see the significance there so clearly. Because of course, Mathematica has the function integer name. Yes. So I guess I can do this. Never used this function. Okay, let's and then select from these where the last string free E. So basically you have 2, 4, and 6, and then between 30 and 66. So this is just a speed optimization, because also for these it's 2, 4, and 6, because 1, 3, 5, 7, 8, 9 all have an E in them. So basically it has to end on 2, 4, or 6. Yes, or 0 in this case, of course. So that's what they check here. So I'm just curious how they handle 0 expand. Yes, but how does that done here. Let's see. Let's see how, because 60 is allowed, but like, let's say 0 is not. So let's say it's 60. Well, the thousands, the remainder is between 30 and 60. Then we take modulus 10. That's a bit weird, because I think this function would return 0 to be E3, but actually it is not. Let me see if so if the remainder is 0, so it will not be in this range, actually. So it will not do anything. So if it is, yeah, I think this function is bad for 0, but we can add that case. Although I think maybe 0 is not considered. Yeah, I think everyone starts from 2, so we can make the function that also accepts. Which one did I? Auto hotkey was the one I was looking at. Okay, let's just be lazy and copy them. I'm not familiar at all with auto hotkey, to be honest, but I guess we can translate it. So I'll just be lazy and kind of copy this this code to the Mathematica language. So all these codes are basically the same. Of course, the brackets are different and things like that. So floor and mod, I think we could use quotient remainder. That might be, let's see if that is exactly what I want. So if I did 15 here and I do 4, so I get, okay, 4 is maybe not a good, let's say an 8. So it's multiples of 8, so that will be this floor part, and the remainder is this part. It's okay. Yeah, maybe that's a bit faster. So what we can do is we do b comma r equals I 10 to the power 9. And then this will be mr, this will be tr, of course the input here will be m. So let's make these variables here br, t, m. Well, if, so in AutoHotkey with many other languages you have to write this in 2 equalities, and so in Mathematica what we can do is write it as 1, so we could do this, and m equals mod m comma 10, so that we can write in one go, and we do the same for t, and we do the same for r. So note that this function will not work for 0, but well, we don't test that. And then, so we want to test it if it's 0, 2, 4, 6. So maybe let's do a little, because it's like 4 times the same code. Let's call it 0, 2, 4, 6, q, where I think that's an integer. and n equals 0, or n equals 2, or n equals 4, or n equals 6. I'm not sure if brackets are needed, but somehow it makes me more comfortable. So let's see. 2, 4, 6. Well, and 0, but 0 is not included in this range. Here we go. Yes. If for B and for M, and so note that I will use this one. So this is a neat symbol for AND, but once I copy it to the Rosetta code, this will not be so convenient. So all these are satisfied, and note that Mathematica, if it fails this one, it will not test this one, and so on. So it is short circuiting, as they call it. So we do add one to the counter, and then if show print I basically. Not sure why there's a semicolon here. Let's see. Okay. It does not print it here. What it does is it starts with an empty string, and what it does is like it appends to the output string. So let's see. I guess the dot equal is appending, and then this is like a ternary operator, I guess. So show. I'm not sure why. What happens? Is this like the help for show? Huh. Oh, I didn't know that they implemented these things. So I guess this is so if show is true, it does this. Otherwise, it does that basically. Okay, yeah. I and to string I and a space, and then and then here, do I want to print it? Let's just print it. Min max colon output count equals counter. Okay, now it's the big question, does it work? So 1/3000 in steps of 1. So there's one that should be true in our case. This looks a bit too much. Let's see what happens. Because the hundreds, it should not work. Let's see. Okay. So this is the problem, or one of the problems, let's say. So why do the hundreds work? BMT, BMTR, BM. Because this is a remainder. Okay, let me just do print R. Let's just do I++ for now, because I think it has some optimization. Oh, I'm printing now. It only does odd one, even one. Sorry, but I guess. So the minimum should that always be then an even number for this code to work. Okay, let's see. So this will be input I, okay, this might be, so let me save this code just to be sure. Eban numbers. So that is always 0. So let's see. Let's see, did I do this correctly? This, well, probably doesn't matter, but oh, it does matter. Yes. Okay. So why was it R? So if this is M. Okay, yes. So we have 18 numbers, 19 they have. That is peculiar. Because I guess it should do this. Yes, so it includes also 2. Let me add a little space here. So 2, 4, 6, 30, 19. Okay. And then the second range is from 1,000 to 4,000. So then, okay, it's 21, yeah. Let's say from 0 actually. What were the powers I had to show? 10 to the 4. 5, 6, 7. 5, 6, 7. But let's not output this. That will be very long. Okay, let's go back to, what was I looking at? Auto hotkey. 79, 399, 399. Why is that? 100. Yes, that will all be cut. And then, oh wait, this is million. So now it's doing 10 million. So that will take, I guess, roughly 10 times longer. Okay. Show all output here. Yes, we'll do that. Let's add it. So this is a bit of a different style of solving because, well, you can figure it out yourself, but you can also be smart, well, not smart, but lazy, let's say, and make use of the other solutions that are already there. Sorry, I first need to copy the header, because sometimes the solutions can be relatively easy. So it's good to have some inspiration from other languages. Of course, you need to know some other languages, but this auto hotkey looks a bit like C, kind of. So it's pretty easy to understand for me, at least. So does this copy nicely? Yeah, looks actually damn good. Save this. Save this, kill this. Process, process, process. Okay, let's have a look. That looks all good. All right. All right. A magic constant. A magic square is a square grid containing consecutive integers from 1 to n squared. So 1 to 9 in this case, okay. Arranged so that every row, column, and diagonal adds up to the same number. So 15, 15, 15, 15, 15, 15, 15, 15, okay. That number is a constant. There's no way to create a valid n by n magic square that does not sum to the associated constant. Sure. So 3 by 3, 15, 4 by 4, 34. Traditional, the sequence leaves off the terms n equals 0 and n equals 1, as the magic squares of order 0 and 1 are trivial, and a term for n equals 2, because it's impossible to form a magic square of order 2. Okay. Start at order 3. Show the first 20 magic constants. Show the 1000th magic constant. Find and show the order of the smallest n by n magic square whose constant is greater than 10 to the 1 to 10 to the 10. Okay, that's a bit weird, the superscript there, but sure. Stretch. Find it for 10 to the 11 to 10 to the 20. Alright. Let's open, oh, that's the wrong button. Open a new notebook. Let's save this for Rosetta. Magic constant. Oh, I made a typo. I'll fix it later. So the sum of all the n by n squared will be this. And then the sum will just be divided by n. So yeah, we'll divide that by n basically. So this will be the sum, the magic sum basically. Magic sum for n equals actually I can do this one. Boop. And now magic sum, I don't know, 3 will return 15 as we think, and 4, what is it? 434. That looks very good. So remember that I don't do the semicolon here because then the sum would be re-evaluated every time. So I do this, so when I execute this at the first time, it will assign not this basically, but the answer of this to this thing. So if I do magic sum now, you see that the formula is assigned to this definition, so it does not redo this summing every time I call magic sum. Alright, so the first 20 magic, okay, so do I want to show the order? Traditions, so it's 3 basically the first. Let's see. Traditional sequence leaves of terms and well, the first 20 is pretty easy. So we have to add 2 in this case, and then, so I guess, yeah, that's all good. And then the 1000th, so let's see if they do 1000 or 1002, let's say. Okay, so yeah, okay, so what I can do is redefine what is, if I should subtract 2 always, let's say, so that the first, so I don't have to ask for the third, but for the first in the sequence. Let's do it, let's make a little helper function. Probably not the most efficient, but well, it's okay. Such that now I can just do this, and here I can just do this. Alright, that's pretty good. And now They look for the first above a certain number. I'm thinking, can we solve this analytically? Or do I want to make a function that solves it? Because this is a cubic equation, and that we can invert analytically. Because we want to have it greater than this, so it will. So if I solve it, it will come to some well, something with square or cubic roots in there. But I can just do the ceiling to get the next integer, which will be the next biggest one. But let's just show off, just to give myself an idea what kind of numbers. So this is the first above 100. Oh, that's a bit weird. This is okay. This is -2 again, I guess. Yes, okay, that makes a bit more sense. So they're okay. So this is the order, not the. Okay, so people use different. So what is 1000 and what is the? Yeah, okay. Anyhow. So what did they do? So I'm not so familiar with algol. I do know some Python, for example. So this is a bit nasty, let's say. But we know this. So what we can do is set this equal to some limit. Let's call it lim, and solve it for n. Cool. So that will be, in general, 3 solutions, but 2 of them will get complex. So solve values I can do. Let's call this the solutions, and then and then the solutions will fill in the limit to be, for example, 10 to the power 12. And so what I can do is now, well, let's do first n to see, so I think it's always the first solution, but what I can do is do the ceiling, and then, well, basically it's always the first solution, because here you see there is an I here, which will turn these things complex. So basically, I'm not sure if you can say reals. Does that do anything? No, okay, I don't want that. I think I just want to have this one. So what we can do, inf magic sum, and then the input is limit, is this thing. And well, probably I want to do, sorry, I called it lim. That's fine. So if I do 10 to the 12, okay, and then of course I want to take the floor of that. I want to take the ceiling actually. That is pretty neat, I would say. I mean, lim does not have to be a single number. It can even be a list. Basically, now I have them instantaneously, which is much better than looking for it in a while loop, because, well, they can take 2.7 million iterations. Well, this can just be, so the stretch is 10 to the 20. I mean, we can calculate them all up to 50. It's it's now very, very trivial, I would say. So I don't know if more people did that. So let's output this in table form. Table form, and then we want to do table headings automatic. Or do I want to show 10 to the power that number? Okay, let's do that. So nums equals this. Let's transpose that, and then table. Well, it goes to the grid. It's easier. So maybe okay. Let's call these exponents, because otherwise this gets a bit ridiculously big. So the numbers are that, but then the what we do here is superscript 10, comma. So that is a bit better in terms of legibility. Does more people do than 20? So I'm not sure if other people do the inversion. I think all people do some kind of. Oh, here, no, so this guy. Again, I'm not familiar with. I'm not even sure how to pronounce it. Fix or fix. But here it also takes cube roots. So then there are order, goal, magic. Yeah, I'm not sure how that works. But looks as if people don't use basically this method. But it's good. Then in that sense we show something new, which is always good. Because this is also the fastest way of doing it. Click, click. So let's save it, and then let's add it. Oh, I'm sorry, I didn't increase the size, but well, it's a bit too late now. But so here we have to. Oh, did I do that correctly? Yes. And then we copy these. So I hope this one copies nicely. If it does the power well, yes. Yeah, let's keep an enter there. We can even check, of course. So if I do this number, and I say magic sum, no, magic sum, this one, I see it's just above, well, if I do -1, oh, is that correct then? Okay, yeah, I have to, because the magic sum, here we go. Because of this difference in the order that people use. But let's just check 10 to the 10 is 2715. 2715. 2715. 2715. I think now the order at least is correct, but for the other one, some people use other orders, let's say. Alright. Then this one is done. Do I want to do this one first? Yeah, sure. Smallest number k such that k plus 2 to the power m is composite for all m less than k. generate the sequence of numbers a key for a of k, where each k is the smallest positive integer, such that is composite for every positive integer m less than k. Suppose k is 7, set m equals 1 to 6. If any are prime, the test fails. So false, okay. It's only necessary to test odd natural numbers as an even number. It's only to test odd natural numbers. An even number plus any positive, yeah, okay. First 5 elements of this sequence. Oh, so this is probably a harder task because there's only 6 solutions. Well, either hard or very new. We can actually check that. Look at the history of this. So it is a very new assignment. So it started January this year by Thundergnat. All right. So let's see what other people do. It's always interesting to see, but I guess it will just be brute forcing it. So Ren, I know a little bit. Yeah, okay, we'll just brute force it, I guess. So let's open your notebook and we'll make it larger this time. Okay, I'm not sure how to call this. Okay, Rosetta composite numbers or so. I don't know exactly how to call it. Valid k. What input is k? So we want to have all true. Well, I can first do if even q k return true, otherwise, and here none of them, let's see, so all of them should be composite, all true. And what should be all true? So here I'll do the powers, so range, so let's see, m is less than k, so from 1 to k minus 1 basically. And what should be true? Composite q k plus 2 to the power hash. I think that is it. We can even remove the module. Let's first see how performant this is. Sorry, this is false. And so I'm not sure if it's defined for 1. So the first should be, okay, maybe it's better to do this. Select from 1000. Here we go. So I don't know, 1. What happens for 1? That is 1. 2 to the power zeros. 2. 2 is wait, if that k is 1, then there's nothing to test. It's a bit weird what to do with, because if k equals 1, then m, well, m doesn't do 0. So this would not iterate over anything, so that would indeed give true. Okay, maybe I have to make an exception. 0, false. True, no. Sorry, 1. Here we go. But what do I want to do? Find the first 5. So How long does it? Okay, so we need to go up to 6,000 or so. Let's see how long that takes. Okay, not that long actually. Found, or let's call it list. Do. Oh. 1 to infinity. Or, yeah, then I have to know an upper bound. If valid k I, let's use k here. I mean, I use I here, but let's use k because it's valid k, so it's a bit nicer. Append to list, no, list k. If length list bigger or equal than 5, break. And then here we can do, well, list is also fine. Let's do, just for my entertainment, let's show this in the meanwhile, so we know where it is currently at. But let's find a few more. Let's see. First 5 elements. So there's always probably, okay. So people only find really the first 5, because I can imagine that this gets really hard, because the number of digits, well, 2 to the power of some number is roughly this number divided by 3, so it's like 3,000 digits, 4,000 digits numbers. But checking if they're a composite, of course, is perhaps easier than testing if they're primes. Well, anyhow, let's optimize this a bit. This will not help a lot, but it will help a tiny bit. Yeah. Let's see, 2, 4, 6, 8. Let's solve for 8. So there's not so many languages yet. That's always very nice to contribute to upcoming languages, let's say. So we can copy the code. Copy. I will remove the dynamic. So this line will be not in there. Well, I'll clarify. Okay, let's see how long this takes. Performant? Is that a word? Functioning well, yeah, okay. That looks a bit weird somehow. I found the first 8 of this sequence. So you also have the Euler code. The Euler project, and there the rule is always less than a minute. So here we're 20 seconds, so that is, let's say, reasonable. Yeah, that looks good. Save page. All right, let's see what it looks like. Okay, that looks yeah, very compact because you have this all true basically, and so this will check all these k's, or this M here basically, and if the first one is false, then it immediately stops this thing. So it's a very efficient and neat way of coding. So I always like some of these with primes. So let's save this anyhow. Rosetta prime triangle. So you will require a function f, which when given an integer s will return a list of the arrangements of the integers 1 through s, such that g1 equals 1, gs equals s. Okay, and generally for n equals 1 through n s minus 1, n and n plus 1 is prime. S1 is undefined. For s2, print f as has to form a triangle. Then again, to s, print the number of possible arrangements meeting these requirements. Oof. Is that a stretch goal? Oh, so this is the number of ways it can be done. Oof. So you see here already that this becomes pretty big. So, well, for the first 10 or so you could just brute force it. But after that, this becomes quite tricky. But let's just do it for 6 just to see if that would... so this will give all the permutations. And now we select from those. We actually don't need that. Where so the sum of all of them. How do I do that? Most plus rest, all true, prime q. Is that correct? Okay, yeah. The first has to be 1 and the last has to be, okay. Perms. So actually what I should do is from 2 to, well, let's say 5, and say perms equals join 1 dash 6 so for 1, 2, 3, 4, 5 there's a 5th, yeah, so it's a 5th here. Okay, so well, let's go a little bit higher. It's 4, okay. Let's go 1 higher. I think that should still be, 7. Okay, let's do 1 more. Then 10 factorial is already pretty big. See? Well, it's a little bit less because the first and last numbers are fixed, but this is 24. So the first couple are pretty easy to find. But for this 20 factorial, well, it's actually 18 factorial. Yeah, that's a big number. We cannot check all of those. But of course, the choices here are very limited, so I'm thinking of some kind of recursive function. So this is approach, let's say 1, which works, but not for big numbers. Yeah, so 11 it will work. Let's say 12. This will already take quite a while, I guess. 216. So it does work, but the problem is we cannot go through million, billion, trillion, quadrillion, 6 quadrillion possibilities, at least in not anytime soon. So we need to make a function that does this in an efficient manner. I'm just thinking how to do this. Alright, find prime triangles. Let's call this max. So how is it called there? S. Do I want capital S? Is that used somehow? For now S? Let's call it max. I think max is somehow better than so basically here we have a start and here we have a remainder. So here we call, probably this function has to be in there actually. Yeah, let's put that one in there. I'll show you later why. We anyhow clear it. So here we make a variable I equals of let's say C or count equals 0. Yes. So we define this function inside, and then we call it with, so the start would be 1, and the remainder, well, and maybe, let's also give max here. Oh, max is now doubly defined. Well, we can call it max. That's also fine. Remainder would be range 2 to max minus 1, and the max will be max. Okay, and now here we say count. Yes, so here we say if remainder, length of remainder is bigger than 0, yes, then let's call here last. Last equals last of the start. So this will be the first piece, so up to some point, let's say, so I'm here, for example, so it takes 7, so they say, no, this is a prime, this is a prime, this is a prime, this is a prime, so then I take 7, and then I find from these remaining integers that I have left, which one will be situated at the prime. So basically, I want to select from remainder those for which that this is prime. So these are nexts, let's say. So do, oh shit, n goes over nexts, and then we call new start equals append start comma n. So this will be the new start, and new remainder equals, oh, this is not so nice. Maybe I do it differently. This is okay. I just go over the remainders. Do I want remainder? Yeah, it's fine. If last plus r is prime q, probably I want to do the index rather than this thing. So there will be remainder ri. So if that is true, I guess we have to put all this in there. So the new start is the last start plus, let's do this for easy accessibility, r. So new will be r, and the new remainder, now this is much easier, so we can do delete remainder comma ri. Is that the delete the element at position n? Yes. Okay. So new remainder, and the max stays the max. So if there's no remainder remaining, then we do count plus plus, right? If there's no, did I check the last one then? So that one is added. Yes, count plus plus. New start. Okay, I have to make these all local variables because now it is a recursive function, so I have to be really careful. I would be surprised if this works in one go, but let's see. I think I might have to do this. Here we go. And then, well, let's start off with a small number. Save. 2. Okay. So what I can always also do is print start here. 1, 2, 3, 4. This is 5, 7. And the last, because I don't add the last one. Okay, so if it's 0, then I only have to check still if the last two form a nice sequence. That I still have to do. So there's no remainder, because the last one should always be max. So if the last one of start plus max prime q, then here we go. Append start comma max count 1, 4, 3, 5. Okay, so 6. Okay, 7. It's 2 solutions. 2, 3, 4, 5, 6, 7. Yeah. 8. 9. Okay, 10. So of course this print becomes kind of annoying. Let's call it fourth solution equals blah. I don't need to do this. If count equals 1, print this bad boy. So only show the first one, let's say the lowest one. Okay. Is this number correct? 3392. Seems pretty good. So the first solution, but of course it wants to count all of them. So what I can actually do, which might be nice, print temporary dynamic of count. Not sure if that works. It becomes red. Not sure why it becomes red. But these are the number of solutions now for 17. It should be, was it 13,000 or is it this one? How high should I go? Up to 20. 59,000. Hey, wait, 17. Do I do this correctly? 2 minus max. So they call this 1. Wait, how many numbers is this? So this is 18 term. I could have seen that. That is 18. Yeah, okay. So the 20th. So did he just not fulfill the full task? Okay, he didn't do the full task. So this very performance C code does the full thing in half a second, which is very impressive. So I'm not sure if we can do that. We could try compilation. Also this primality checking. Yeah, I'm not sure how if we can improve that, because all the primes will be less than, well, basically s plus s minus 1, or 2 max minus 1. Can I do that? So primes equals prime pi, let's say 2 max, range, prime, bracket. Did I do that correctly? Yes. So these are the possible primes for that max. In this member queue, does it have an operator form? It doesn't have an operator form for the list one. Okay, let's say max equals 100, 1,000. Then I have all the primes up to 2,000, let's say. And now I say primes true, append underscore false. Okay, I have to thread this. Here we go. And now we're gonna use dispatch again that we've used before. Let's call it DP. And now let's do some random integers from 1 to 2,000. And let's do 100,000. And then select of so what I can do, prime q of ints, and then count count true. That is pretty damn fast. But I can also do this. Wait. Ooh, this thing is a bit too... Actually, I can just leave this off, maybe, no? If it's true, then otherwise, yeah, okay. Well, this gives the same results, which is, of course, very good. The question, of course, is which one is faster? But let's do a big... So it's not that much faster, actually. because I would expect that prime maybe for small numbers already has some optimizations in there. And then the question is, well, actually this will be a very low number, huh? Yeah, it's 50% faster, but it's not, you know, as fast as I would hope. But maybe what I can do so these are the two max. I have another idea. So we do prime q of all of these, and then prime q of n is just primes n. So we can do this and this. I mean, it doesn't go much faster, unfortunately. I'm not sure if this counts, if that really speeds it up. Yeah. All right, let's do this thing. Loop table. How do they call this? Is this N or S? From 2, let's say 2 to 10, just to test it out. Yeah, okay, what we can do now, 20. So it will run for a while. So I'm not sure why these two stay, but not asking anything. So these will stop at 18. This C goes to 20. Use bit patterns. I mean, they even have the brown sequences. I'm not sure what the hell they are doing here. I guess this is impossible to read. So I'm pretty sure we can do it. The thing is, how long does it take, right? So this already takes, well, quite a bit of time. So of course all these results will, so 18 is found and what, how much was it? 150,000. So this one will take roughly 3 times as long. Well, it's already at 10%, not too bad. So this will eventually finish. Probably this will take quite a bit of time. But the code definitely works. And I surprisingly coded that recursive function in one go, or basically 2 goes, because I forgot that they had to add the max number. Oh, and what I didn't tell you is of course that this helper, since I want to increment this counter every time, of course I can have an external variable, but it will be a bit, let's say, nasty. So what I can do if I implement this function inside another function, I can have this one have a local variable, which this then will increment. So that's why we have a function definition inside a function definition, and then I can also call it here. Yeah? And this is now with this little optimization here for this primality testing. So rather than, so I don't know how it's implemented in PrimeQ, of course, but we are very specific to only to integers up to some small number, let's say 40. So so the number of primes below 40 is relatively low. So how much should this be? This should be 480,000. Okay, we're almost there. Anyhow, I think I will stop here. I will leave this running. It will take a few minutes to finish this one. So this one gives us a solution, and then well, once it's done, all these counts will be gone because this is uses print temporary, which will I will actually remove here. And once it's done, I'll paste the solution here, and we'll be very happy. Thank you all for watching. See you all around.